So some of the RTOS services, so here I show a time delay or sleep. So a task is an infinite loop, while one, and here I basically say I would like to sleep for n number of ticks. So assuming my resolution of ticks is 1 millisecond, whether or not it's dynamic tick or not doesn't really matter. If I say it's 1 millisecond, then I could say I would like to delay my task for 5 milliseconds. So you specify in this case 5. And then the task is put to sleep until 5 ticks of time expire. So 5 milliseconds of time expires, that task will now become eligible to run again. And the RTOS will decide if that's the most important task. When it wakes up in 5 milliseconds, it will get if it's the most important task, it will get the CPU. So it could be used to actually schedule, if you want, regular tasks that are running at regular intervals. So control loop, updating a display, scanning a keyboard, letting other tasks a chance to run, and so on. So these are things that you could do by saying, okay, I'm going to wait. I don't need to do anything for a whole 50 milliseconds. I'm going to put myself to sleep, and the task doesn't consume any CPU time at that point until the 50 millisecond expires. Most RTOSs also offer a software timer. So there's a task dedicated in the RTOS that manages software timer. And then software timers could be either one-shot timers or auto-repeat or cyclical timers. So in the case of the MicroSUS 3, you could specify, I want an initial delay of this much time, and then start decrementing my timeout. This is my initial, okay, create the timer, start the timer. There's an initial time, and then from that point on, we go and repeat on a regular basis. At expiration of the timer, a callback function is called, and that callback function is something you as a programmer decide what it does. So in the case I show an example, like my task opens up a valve, I start a timer to close the valve after X seconds. It's a big industrial valve and it takes a while to close. So I don't want to continuously pull the limit switch. I may just want to close. I know I need to close it in a certain amount of time. And when the time expires, then I could say, come back and make sure that the switch in fact confirms that the valve is closed. So an RTOS provides you this capability, and you could have an unlimited number of timers, and the limit is only based on the amount of RAM that you have, because each of these timers has a timer control block, if you want, that contains what's my initial period, my initial delay, and what's the period, what's the callback function, and so on. So there's a whole bunch of things you specify. Another RTOS services is to use what's called a semaphore. So a semaphore used to be used for resource sharing, and I'll show you why most RTOS vendors don't recommend using a semaphore anymore for resource sharing. So what I bring up the definition of an RTOS object. An RTOS object is the semaphore itself, and the semaphore itself contains a value. It contains a list of tasks that are waiting for the semaphore, and it contains a counter, if you want, what's the count of the semaphore, kind of too many details. But so the idea is that each task that wants to access a shared resource would have to go through, I need to get the access to the semaphore. And if somebody already owns that semaphore, that key, then that task will have to wait until that semaphore is released. So I would then, once I grab the semaphore, once the key is available from the RTOS, then I actually would access the resource. And then when I'm done with the resource, I have to relinquish the key back so other tasks could have access to that semaphore. So all these three tasks are competing to get access to this resource, but only one of them will have access to it, and the one that gets it is the one that initially gets the semaphore in the first place. So the reason I say people don't use that anymore is because of a problem called priority inversion, and that occurs when you're using the regular semaphore. So this is what happens: a low priority task occurs, an event for a high priority task occurs. the high priority ISR, task ISR, executes, signals the task, we execute the high priority task. The high priority task all of a sudden says, oh, I'd like to have access to that resource, so I need to grab the semaphore. But the semaphores are already owned by the low priority task here in yellow. So the high priority task is suspended because it cannot execute anymore. It doesn't have the event, in this case, the semaphore, that it needs to continue. So the low priority task executes, and then as it's accessing this resource, another interrupt occurs, but this time it wakes up a medium priority task that has nothing to do with the semaphore, the resource. It does something completely unrelated. The medium priority task executes. As soon as it's done, we go back to the low priority task because it's waiting for its event to occur. The low priority task finally relinquishes the semaphore, and then the high priority task is able to run because it was waiting for that event. It was waiting for the semaphore release, and then the high priority task gets to execute. And when it's done, we go back to execute the end of the low priority task. So what I'm getting here is that the fact that this medium priority prevented a high priority task from executing, which kind of defeats the whole purpose of the RTOS. So this is called an unbounded priority inversion, because there could be any number of medium priority tasks that could occur that would interfere with the relationship between these two tasks. So to avoid that, there's a new mechanism that's called a mutex, or mutual exclusion semaphore, that was designed specifically to correct this problem. And again, a mutex is another kernel object. It's another object that is provided by a bunch of services. So there are API calls that the kernel provides or the RTOS provides. And same scenario, you use it exactly like you used to use semaphore. You acquire the mutex, you access the resource, and then you release the mutex when you're done. So, anyways, so this is used more to prevent priority inversion because it has what's called built-in priority inheritance. So same scenario as the previous idea with the semaphore, except this time we're using a mutex to access a shared resource. Low priority task executes. It's preempted by an ISR that triggers a high priority task. The high priority task says, I'd like to have that resource, but it's owned by a low priority task. So what I'll do is I'll raise the priority of this low priority task temporarily while it's accessing the resource. So even though an interrupt occurs from a medium priority task that's waiting for that event, as soon as the ISR completes, it will say, is there a more important task that needs to run than the one that was interrupted? And the answer will be no, because I was running this low priority task at a raised priority, and thus it's more important than the blue task. So that will go back to run the low priority task until it's done and it relinquishes the resource. The mutex goes back to the high priority task as soon as the mutex is released. The high priority task executes. When it's done, medium priority gets to execute, and finally the low priority task gets to execute. So whenever you're sharing a resource between multiple tasks, you're better off to use a mutex mechanism, which like I mentioned, most RTOSs have that capability. Now, another service provided by the kernel is a semaphore, and now semaphores are mostly used as a signal. So an ISR or a task could send a signal just saying, by the way, the event that you're waiting for just occurred, and then the RTOS gets to schedule the task. If it's the more important task, it will get to run. So the whole purpose of that signal is just a signal. There's no data being transferred. There's no information being transferred. Both the sender and the receiver have to agree that whenever that event does occur, it means such and such a thing. So somebody pressed a key on the keyboard. Okay, the task is going to read which key was pressed. I don't know which key was pressed yet. The task will determine that. All I know is somebody pressed a key on the keyboard. So that's the semaphore use. So that's why you would use the semaphore event. A lot of RTOSs nowadays, of course, MicroSUS3 includes that, signaling a task or using an event flag. So an event flag is another kernel object. It contains a series of bits. Each one represents an event, so 0 or 1. So a task or an ISR could actually set or clear one or multiple bits. And then whenever the bits that a task is waiting for, so whenever all the bits, because there's a wait for all API call that you would specify, so wait for all bits to be set. So then whenever all the bits that this task is waiting for has been set by either ISRs or task, then that task will be able to execute on the CPU. There's a little timeout hourglass here that shows that this task is willing to wait for all of these bits to be set, but only for a certain amount of time. That's assuming, of course, that you have a system tick and then you're running the capability of having timeouts. Another task could actually say, I would like to have any one of many bits. I could say I want 5 bits, but any one of those, as soon as one of those happen, I want to wake up the task. And again, same scenario. If none of those bits are set within a certain amount of time, then that task will get to execute. So that's one of the services, the event flags, and it's called different things from different RTOS vendors. So another way to actually use the RTOS is an ISR or a task could send a message, in this case by reference. So here, here, for example, we have a message queue object. A message queue contains pointers to data. So this data somehow needs to be produced by whoever needs to send the data. So you get that from a fixed size memory block manager or heap manager that is RTOS safe. You would get a fixed size data block. You would populate that data block and post or send the message containing the pointer to that data to a task. And of course, the task understands that whenever I receive a message from this message queue, it has a specific format that I will understand, and I will thus know what to do with this message. What the message is, it could be, here's the Ethernet packet I just received from my Ethernet controller. And of course, the task that's going to handle that packet knows exactly how to decompose the Ethernet frame. So that's one of the features of most RTOSs. One way to actually implement RTOS services is to actually dedicate a server task. So you basically have a task that gets requests from other tasks or ISRs and says, okay, I would like to do something specific. Don't have an example of that right away. So I would like for this server task to do something. Here's what data is associated with what I would like to request. So presumably the request contains a command, if you want, at the beginning of the data that you're sending, plus a piece of data that goes along with that command. And the server task is responsible for performing the operation that's been requested by any of these tasks or potentially an ISR. And a task could actually wait for a response if that's the way you design your system. So the server task executes your request and sends a response back to your task, indicating either success or failure of what you've done. So that's pretty much most of the RTOS services that you'll find in most RTOSs. I'll get into talking about process separation and the use of using an MPU or MMU, memory management unit, or memory protection unit.